Our video today will be about integration by part. Integration by part is one of the techniques used to evaluate integrals. The integration by part is the inverse of the product rule of differentiation. We can easily prove the rule of the integration by part starting from the product rule of differentiation. The rule of integration by part states that if we have the integral of product of two functions, let's say that the first function is named by u and the second function is named by dv. The rule states that integration of the product of u times dv equal uv minus integration v du. To memorize this rule, we can say that we have the first function which is named by u and the second function which is named by dv. This function is differentiated and its differential du, and this function is integrated to calculate v. So the rule of the integration by part now is u times v, the first term, minus integration v du, that is the second term. So using this table we can memorize the integration by part rule. U times v minus integration v du. Please note that the integration by part rule change our integration to another integration, but instead of integrating u, we integrating du. And that's the key of when we use the integration by part rule. If the differentiation of the one of the two functions makes the integration easier, we select this function to pu and get its derivative and integrate du instead of u. But the second function, which is named by dv, must be integrated because we need v, not dv. So we must be sure that the second function can be integrated. To understand the rule of integration by part, let's see an easy example. If we need to evaluate the integration of x e power 2x dx, of course, if the function x is disappear, this integration will be an easy integration because the integration of the exponential e power 2x is e power 2x over 2. So we select the function x to pu because the differential of x du will be 1 dx. And as we select u to px, we are forced that dv will be e power 2x dx. And of course, the integration of dv, which is v, is half e power 2x. Now, using our rule of integration by part, the integration will be half x e power 2x minus integration v du. And one of the important advice that when multiplying v du, take the constant outside the integration, so half is outside e power 2x dx. Now our integration will be half x e power 2x minus half the integration of e power 2x is e power 2x over 2. Please note that we select x to pu because if x disappear, as you see here, x will be 1, the integration can be evaluated directly. So the selection of u depends that if the derivative of one of the function makes the integration easy to be evaluated, we select this function to pu, but we must be sure that the second function can be integrated to calculate v. Now let's see another example. If we need to evaluate the integration of len 2x plus 1 dx. Of course, there is no direct antiderivative for the function len. If we think about integration by part, we need this function len to disappear to evaluate the integration. So we select u as len 2x plus 1, and you can think that len is multiplying by 1. So dv will be 1 dx. And now calculating the derivative of u, which is du, it will be 2x plus 1, the derivative of len, times the derivative of the argument inside the len, which is 2, and the integration of dp will be x. Now using the rule of integration by part, our integration is equal to u times v, x times len 2x plus 1, minus integration v du, which is 2x over 2x plus 1 dx. Now the function len disappear, and we have a fraction of x power 1 in the numerator and denominator, so we can easily adding 1 and the minus 1, and then we divide this fraction into two fractions. The first term will be x len 2x plus 1 minus 2x plus 1 over 2x plus 1, which is 1, minus 1 over 2x plus 1 dx. And now this integration is easy to be calculated. The integration of 1 will be x, and this integration is len 2x plus 1 times 1 over 2, which is the derivative of 2x plus 1. Let's see another example. If we need to calculate the integration of tan inverse x. Again, there is no antiderivative function for tan inverse. And if we think about integration by part, and of course also we need the tan inverse function to disappear, so we select u as tan inverse x, and now we have dv as 1 dx. Again, the differential of u will be the derivative of tan inverse, which is 1 over x over 1 plus x squared dx, and the integration of dv will be x. Using the rule of integration by part, our integration now is equal to x times tan inverse x minus integration v du, which is x over 1 plus x squared dx. And this integration can be calculated directly because the numerator can be the derivative of 1 plus x squared if we multiplying 2 and dividing by 2 outside. So this integration will be equal to len 1 plus x squared plus c. Now, if I need to sum up the cases we see here to use integration by part, until now we see two cases. Case number 1, if we have an integration for a certain polynomial x power integer times a certain function, but this function can be integrated. In this case, we select the polynomial to pu as the example of multiplying x times e power x, integration of x squared times sine x, and so on. We have a polynomial times a function that can be integrated like e power x, sine x, and so on. Case number 2, when we have the integration of a certain function that has no antiderivative, like the integration of len times x power n, say, or the integration of any inverse trigonometric or hyperbolic function, like the integration of tan inverse. In this case, we select the len or the inverse trigonometric function to pu to make this function disappear. Let's see another example. If we need to evaluate the integration of x power 3 times e power negative x dx. Sorry, x power 2 times e power negative x dx. Now again, you can think that's case number 1 in integration by part, because we have a polynomial which is x power 2 times a function that can be integrated, which is e power 2x. So if we select x power 2 to pu, and e power negative x dx to be dv. So now du will be the derivative of x squared, which is 2x dx, and v will be the integration of e power negative x, which is negative e power negative x. Using the rule of integration by part, our integration will equal to u times v, so it's e power negative x times x squared, minus integration v du. And again, we can have the constant outside, negative 2, so it will be now plus 2, x times e power negative x dx. Again, we still have multiplication between x and the e power negative x, but please note that the power 2 is now power 1 because the derivative of x squared makes this function to px. Use integration by part again. We can, to evaluate this integration, we can select u to px, and the dv will be e power negative x dx. And again, du will be 1 dx, while v be negative e power negative x. Our integration now, this first term is the same, negative x squared e power negative x, plus 2 times, using the rule of integration by part, u times v will be negative x e power negative x, minus integration v du, and again the constant which is negative outside, e power negative x dx. Now this integration is an easy one. We have, and we can expand 2 inside, 2x e power negative x plus 2. The integration of e power negative x will be negative e power negative x plus c. Now that is the answer of the integration. We can classify this problem as case number 1 of integration by part because we have a polynomial which is x squared times the function that can be integrated e power negative x. But in this case, which is case number 1 only, we can make the integration by part in an effective way, which is called Tabular method. And don't be confused, the Tabular method is another way to write the integration by part in a most effective way, but it only work in the case number 1, which we named the case number 1, which we have a polynomial times the function to be integrated. In the Tabular method, we make a table and we write the polynomial in the left column and the function which will be integrated in the right column. We differentiate this polynomial until it will be 0. So the first time it will be 2x, the second time 2, and third time will be 0. So we differentiate 3 times. Now we integrate this function with the same number of different derivatives. So the first time it will be, after integration, negative e power negative x. Again, second time it will be e power negative x. Another time it will be negative e power negative x. And then we write our integration as starting from the polynomial x squared, this function times this function, minus this function times this function, plus this function times this function. So the integration will be negative x squared e power negative x minus 2x e power negative x plus times the negative, it will be negative 2 e power negative x plus c. Now we write the answer directly using the Tabular method. It's a very effective method, but this method is only work in case number 1 of integration by part, in which we have a polynomial, so the derivative of this polynomial will be 0 after several times of differentiation. Of course, we can use a traditional way of integration by part, as we see for this example, or we can use the Tabular method and write the integration directly. Now let's see another example. If we need to evaluate the integration x times 6 square x dx. Of course, that's case number 1 for using by part, when you have a polynomial x times a function that can be integrated, which is 6 square x. So we can select u to px, and the dv to be sec square x dx. Now we have the differential du, which will be 1 dx, and the integration of dv, integration of sec squared, is tan x. Now our integration using by part will be x tan x minus integration v du, which is the integration of tan x dx. And the integration of tan x, if you are not remember the integration of tan, you can think about tan. It's a sine x over cosine x. And of course, sine x is the derivative of cosine if you multiplying by negative and the negative outside. So this integration will be negative ln cosine x. So it's plus ln cosine x plus c. Of course, we can, another solution, we can use the Tabular method and use right x in the left column and sec square x in the right column, differentiating x to until be 0. So the first time it will be 1, the second time 0. Integrate sec square twice, so it will be tan x in the first time and the negative ln cosine x or ln sec. And using the Tabular method, this integration will equal to x times tan x minus integration negative times negative will be positive 1 times ln cosine x plus c. We see that's the same answer we get it from the traditional way of integration by part, or write it in a Tabular method. It is the same answer. Until now, we see two cases in which we use the integration by part. Case number 1, if we have a polynomial times a function that can be integrated. Case number 2, if we have a function with no antiderivative, like ln, tan inverse, sine inverse, and so on. There is another case that we can use integration by part. Let's see if we have an integration of e power 3x times sine 2x. Of course, this integration is not one of the two cases we mentioned before, because the function exponential e power 3x, it will be the same after its derivative or integrating infinite time, and also the function sine 2x will not be disappear after derivative of integration. But this function sine 2x, if we differentiate or integrate twice, it will be returned the same. And the exponential, if we integrate or differentiate twice, it will be the same exponential. So if we made by part twice, so this integration, we expect that this integration will return to its original form or rotate to its original form again. So in this case, we can call this integration as a rotation integration. Rotation here means that this integration will return to the same form after performing integration by part many times. So if we apply integration by part and select u will be e power 3x and the dv will be sine 2x dx, and differentiating the function u, it will be 3 e power 3x, integrating v, the integration of sine, it will be negative half cosine 2x. And first we assume that the value of our integration now is I, the integration of exponential times sine. Applying the rule of integration by part, I is equal to the product between u and the v, negative half e power 3x cosine 2x minus integration v du. And if we get the constant outside, it will be plus 3 over 2 e power 3x cosine 2x dx. Again, if we make integration by part second time for this integration and selecting u 2p e power 3x, and the dv as cosine 2x dx. We can have now du, which is 3 e power 3x, and the v, which is equal to the integration of cosine, which is sine 2x times 1 over 2. Now our integration will equal to, the first term is negative half e power 3x cosine 2x plus 3 over 2 times u times v, which is half e power 3x sine 2x, minus integration v du, which is e power 3x sine 2x dx, and the constant outside, which is 3 over 2. Now, as you see, this integration is the same integration which we assumed its value to pi. So we can write the answer of this integration to pi again, and after expanding 3 over 2 inside the bracket, it will be 3 over 4 e power 3x sine 2x minus 9 over 4 I. 3 over 2 times 3 over 2, it will be minus 9 over 4 I. We can collect the I again now in one side. So we have I plus 9 over 4i, which is 13 over 4i, equal to negative half e power 3x cosine 2x plus 3 over 4 e power 3x sine 2x. Now I is equal to 4 over 13 times this term plus c. So we use integration by part to evaluate this integral I, because this integration is a product between exponential function and the sine function, and the exponential function will have its form exponential after derivative infinite times, and the sine function will return to its form after derivative or integration twice. So if we make integration by part twice on this integration, it will be returned again to its form, which we assume that its value is equal to I. So after its form is appear again, we write this integration as I and collecting I in one side to evaluate the value of I. Let's see another example for integrations that can be rotated to each in its original form again. Say we need to evaluate the integration of sec power 3x dx. Let's say that this value of the integration is called I, and also if we write sec cube x as sec x times sec square x, and we select sec x to be u and sec square x to be dv. So the differential du will be the derivative of sec, which is sec x tan x dx, and the integration of sec squared will be tan x. Of course, we divide sec cube into sec square and sec, because sec squared can be integrated to tan, and again sec in its derivative we have another tan, and when we apply the rule of integration by part, our integration I will be equal u times v, which is sec x tan x, minus integration v du, which is sec x tan square x. And from the identities of the trigonometric functions, tan squared is equal to sec squared minus 1. And if expanding sec inside the bracket, we will have that our integration I is equal to sec x tan x minus integration of the first function will be sec times sec squared, which is sec cube, minus sec times 1, which is sec x dx. Now, the original form of our integration, which is integration of sec cube, which its value is assumed to pi, is again appear in the integration, so we can name the integration of sec cube to pi. So we have now that I is equal to sec x tan x minus the integration of sec cube, which is I, and the minus times minus, plus the integration of sec x dx. Collecting I again in one side, we will have 2i is equal to sec x tan x, and the integration of sec is ln sec plus tan x. Now I is equal to 1 over 2 times this term plus c. Please take care that this integration is returned to its original form, which is sec cube, because when we select the sec squared to be dv, its integration give tan, and when we select the sec x to be u, its derivative give tan, and after applying the product rule, v times du, we have tan squared, and using the identity, we can transform tan squared to sec again. To sum up now the cases when we use the integration by part, we can think about case number 1, in which we have the integration of a polynomial times a function that can be integrated. In this case, we can select the polynomial to pu, and the function will be dv. And don't forget that in this case, we can use the Tabular method or use the traditional way of integration by part. And the case number 2, if we have an integration of the function like ln inverse trigonometric function, and in this case we can select ln or inverse trigonometric function to pu. And the case number 3, we think about integration by part if we have a certain integration of a certain function, and this integration can be rotated again to its form after applied integration by part. So in this case, we assume that the value of the integration is equal to I, and after applying integration by part, we have the same form of the integration again, so we write it by I and collect the I in the same side. And like the case of having an exponential times sine or cosine, or like the case of integration cosine cube. Thank you.